Hi everybody. Okay, so in this video, we are going to talk about how we can mathematically define heat transfer, how we can calculate it using some equation. So quick review. What actually is heat? Well, we learned that it's not temperature, right? Those are two different things. Heat is actually energy that's stored inside matter. So generally, heat can only be directly measured when it's transferred. This we can measure using a special tool called a calorimeter, which you will do in your lab this week. But heat is actually something that you can't really measure unless it's in the process of being transferred. However, you can calculate it. So, the amount of heat energy that's transferred between objects depends on three specific things. In these systems, when you are talking about heat transfer between objects without sort of disrupting attractive forces, what I mean by that is you're not making or breaking any bonds and you're not making or breaking any intermolecular forces between molecules. Just a straight up, if I take one object and put it onto another object, they have a difference in temperature and there's going to be a heat that transfers between them. We can calculate it and we can call that heat energy lowercase q. So there are three things that this heat energy depends on. The first has to deal with the amount of particles in an object. So what could that be describing? The amount of particles in an object we're going to call its mass. So how much do all of those particles together weigh? So how do we measure mass? We use a scale. And what units do we use for mass? Grams. Lowercase g. So think about this example right here. If you wanted to talk about the heat energy in two systems, let's say you had two samples of water, and those samples of water are at the exact same temperature. One of them contains 500 grams of water, and the other contains 50 grams of water. So take a second to think which of the samples has more heat stored inside of it. Hopefully you said the 500 gram one. If you think about these samples, 500 grams is significantly more mass than 50 grams. Something that's bigger has more particles inside of it, and the more particles you have, the more those particles are moving, and the more those particles are able to store that energy. So the bigger the mass, the more heat stored in a system. So we're going to say sample A. And I'll leave you to write your because in your own words. Okay, so the second thing that heat energy transfer is dependent upon is something you learned about this week: specific heat capacity, which we define as capital letter C. So a general definition: specific heat capacity is a property that measures the degree to which heat is gained or lost, the degree to which heat gain or loss affects the temperature of a particular substance. So what this is kind of really saying is how good is a sample at gaining or losing heat energy? How is that going to affect the temperature of that substance? So a more specific definition, how it's actually defined, is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So, think about this like one particle at a time. Let's say you have 1 gram of some substances. That mass of that specific substance, you want to change its temperature by 1 degree. So the amount of energy that it takes to do that is defined as that substance's specific heat capacity. I think I said particle earlier. I meant to say gram. Oops. So you're thinking about it in terms of 1 gram. 1 gram of that substance, how can you get it to change, or how much energy does it take to change it by 1 degree Celsius in either direction? That's its specific heat capacity. But in general, really what you're thinking about here is just how good is a substance at gaining or losing heat? How good is it at transferring heat energy? So the way that we can measure specific heat capacity, we're going to have to use that tool, calorimeter, by calorimeters. We're going to practice this skill in a lab. So it's measured by a calorimeter, and there are 2 units that we can use to discuss specific heat capacity. You have joules per gram degree Celsius, or you can use calories per gram degree Celsius. This calories right here is in lowercase c calories. Yes, there is a difference. You may have heard of calories before when you're talking about calories of the food that you eat, right? That's actually capital C calories. Fun fact, one capital C calorie is equal to 1,000 lowercase c calories, or it's equal to 1 kilocalorie. All right. So here's 2 examples for you. Number 1, you have a metal pot that heats up almost instantly. So think like you're making mac and cheese, right? We love boxed instant mac and cheese. Yum. Okay, so we're making instant mac and cheese. You have to heat up your water be able to boil your pasta. That metal pot, if you go to touch it, it heats up really, really quickly. It's so hot to the touch and it heats up really fast. But the water inside it takes forever to boil, especially when you're feeling hungry, right? It feels like it takes even longer than it actually does. So use specific heat capacity to explain why this might be true. Think about it for a minute. Okay, so if something heats up really, really quickly, that means it must have a low specific heat capacity. It's really good at changing temperature. It takes less energy to change its temperature. So when you go and put that over a fire and your fire starts heating up your metal pot, it's going to take that energy from the fire and absorb it really, really quickly, causing it to change temperature really, really fast. But the water that's inside the pot takes a lot longer. It must have a higher specific heat capacity. We saw in our Urban Heat Islands lab that the heat capacity for water is actually really high, right? It's 4.184 joules per gram degree Celsius. It takes a lot of energy to change the temperature of a sample of water. So things that have low specific heat capacities like metal heat up really fast. Water has high specific heat capacity. So I'll give you a second to pause the video and go ahead and write your explanation in right here. Okay, so now let's think about our initial phenomenon. Which of your blocks, the metal or the wood block, had a higher specific heat capacity? You can use this to help you out in your 6.1 lab conclusion that you're going to turn in. So which of them had a higher specific heat capacity? Must have been the wood, right? It must have been the wood because it didn't melt our ice as quickly, which means that it cannot transfer energy as quickly as the metal block can. It takes more energy to change the temperature of the wood than it does to change the temperature of the metal. Okay, so I'll give you a second. You can write something in right here real quick and pause the video. Okay, so that was a long tangent into specific heat capacity, but what are we doing this for again? So as a reminder, we're trying to figure out how we can calculate heat, Q. So the way that we can calculate heat is dependent upon 3 things. We said mass, specific heat capacity, and one last thing now. It's dependent upon the average kinetic energy of the particles in a substance. All right, we've talked about this before. What is average kinetic energy of all the particles in a substance? Well, that's temperature. Temperature. So how do we measure temperature? We use our handy dandy thermometer. And we do this in units of degrees Celsius. Never degrees Fahrenheit. Boo. No unit. Okay, so now let's think about one more example. Two samples of water have the exact same mass, so they have the exact same number of particles in them. Sample A is at 50 degrees Celsius and sample B is at 100 degrees Celsius. Which sample has a greater heat? Well, one's at 50, one's at 100 degrees Celsius. So which of those would have a greater heat? Well, it has to be the one that has 100 degrees Celsius. If you're thinking about why, what we're talking about here is motion of our particles, right? With their temperature, higher temperature means your particles have more motion. So the more moving particles you have, the more heat that you are going to have inside of your system. Particles are moving faster, which is contributing to a higher heat content. So it's going to be sample B. Go ahead and pause the video to write in your own explanation. Okay, the last thing I want to bring up before we move on is I want you to remember back from that Bill Nye video we watched. In that video, he showed you the example of a match versus an ice sculpture, a giant ice sculpture. And what he talked about was which of those had more heat. So the match, obviously lit on fire, is going to have a way higher temperature than an ice sculpture. An ice sculpture has to freeze at 0 degrees Celsius. Once you take it out, it's going to start melting, but most of that ice is still going to be very, very cold, especially compared to that match. And what he asked you to think about is which one has a greater heat. He said it was going to be the ice sculpture, and he's exactly right. So if you have something that has a significantly larger mass than something else, even if that something else, like our match, has a higher temperature, if something is significantly big enough, it's going to have a greater heat content than the match with a higher temperature. All of those particles in that ice sculpture are moving. Remember, everything has motion unless it's at absolute 0 Kelvin. So all of those particles combined with all of the motion of the ice in that ice sculpture contributes to a greater heat, because more particles means more motion, and therefore, even though they're at a lower temperature, they're going to outweigh the amount of particle motion in our match. So it is possible for something, even if it's got a low temp, to have a greater heat content than something with a higher temp, as long as its mass is significantly larger. So one important thing to remember. Okay, now let's put it all together. So heat transfer is dependent upon 3 things. You've got your mass, you've got your specific heat capacity, you can also just call it heat capacity, and you've got temperature. So the way that we write this formula is we say Q, heat transfer, is equal to mass, M, times specific heat capacity, C, times the change in temperature. Actually, I should write change in up here. So you have to track how much energy is being flowing into or out of your system. And you do that by tracking changes in temperature, TF and TI. So the way that we write this is delta T, change in temperature. So this is capital delta, capital D delta, and it means change in. So I can highlight this over here to show they mean the same thing. So informally, this little equation is known as Q equals MCAT, because that's kind of what it looks like. So remember, MCAT is your equation you're going to be using to talk about heat transfer. The other way you can write this out, just so you don't forget, is remember that heat is equal to mass times heat capacity times your change in temperature. You always, always, always need to make sure that your change in temperature goes from your final temperature and you subtract out your initial temperature. Always, always, always TF minus TI. Okay, so let's apply this. Let's say you have a silver bar with a mass of 250 grams and you're heating it from 22 degrees Celsius to 68.5 degrees Celsius. We want to figure out how much heat does the silver bar absorb. Okay, Remember, thermodynamics problems, you're always considering the system and the surroundings. Here's why it gets really important. You have to decide, is your system gaining heat from the surroundings, absorbing, or is it losing heat to the surroundings, releasing? So what we're going to do is we're going to calculate the value of Q, and that's going to help us figure it out. So I always start these problems by listing what I know. I just make myself a little chart, Q, M, C, delta T, where delta T is TF minus TI. Okay, so I'm asked to find how much heat the silver bar absorbs, so I do not know this. But I do need to figure out which unit I want it in. To do that, I look for the other thing I'm told here. The specific heat capacity of silver is 0.235 joules per gram degree Celsius. So that automatically tells me I know what I want my unit of heat to be. I need it to be in joules. Okay, mass, I'm told it's 250.0 grams. Heat capacity, I'm given as 0.235 joules per gram degree Celsius. And then delta T, my final temperature minus my initial temperature. It's heated from 22 to 68.5, which means it ends at 68.5 degrees Celsius. I started at 22.0 degrees Celsius for a total delta T of 68 minus 20 is 48, minus 2 is 46, 46.5 degrees Celsius. Okay, now I can plug into the equation and solve. So my equation is Q equals MC delta T. I don't have to rearrange my equation at all because I'm trying to solve for Q. So I can just plug everything in as is. 0.235 joules per gram degree Celsius. And just like with our stoichiometry problems, yes, I am going to be a pain in your butt and I'm going to make you write out your units. It's good for you, do it. You have to make sure you're writing your units out, because if you end up with a problem where your units don't cancel out, you know you made a mistake. Your units are there to help you. They are good for you. They are your vitamins. You take them and you swallow them and you deal with it. So my grams cancels with my grams. That looks good. Degrees Celsius cancels with degrees Celsius, and I'm left with units of joules, which is exactly what I wanted. So my last step is just to plug it into my calculator. So I've got 250 times 0.235 times 46.5, and I end up with 2,731.875 joules. Okay, so according to sig figs, I would round this to 3 sig figs, right? So with heat problems, I'm a little bit more lenient with your significant figures, because it's actually just more important that you write things out as exact as possible, especially when we start getting to heat calculation problems at the end. So if you wanted to round this off, you could write this as 2,730 joules according to the correct number of sig figs. But if you left it like this, I'm really actually not going to be that picky. You can keep 3 to 4 decimals in these heat capacity problems. I am fine with it. If you move on to AP does consider significant figures. It is something important you need to do. So you could also write both of them just to practice your sig figs. Okay, so what is this actually telling me? Well, I got a value of positive 2,730 joules. This is why this is important. I got a positive value of Q. What does this mean? I know that my heat is transferring from the flame or whatever's heating my silver bar to the silver bar. So what this is telling us is when we have a positive value of Q, it tells us that the system is absorbing heat. So use this to check yourself. If you get a positive Q, you know your system is absorbing, which means if you get a negative Q, your system should be releasing heat. So the sign of Q is critically important. And where does the sign of Q come from? It comes from this delta T. This is why you always have to have them in the correct order. Your final temperature minus your initial temperature, that's going to determine your sign of Q. Okay, what you are going to do is you are going to do some practice problems on the next pages. Notice here that I give you the heat capacities of 4 different substances in 2 units: joules per gram degree Celsius and calories per gram degree Celsius. So it's up to you to decide which one you're going to need. The other thing that I've added in here is a heat transfer model and then an explanation to your heat transfer model. So I'm just going to walk you through this section of the first problem so that way you can get a feel for how I want these done, and then you can check in with my answer key, which will be posted in the resources folder of Unit 6. Okay, so this first problem says 5 grams of solid copper 5 grams of solid copper wire was heated over a flame from 20 degrees Celsius to 80 degrees Celsius. How much energy in joules was used to heat copper? Okay, so if we're just thinking about orienting ourselves with what's actually going on in this system, it says 5 grams of copper wire was heated over a flame. So that's what I want to draw out in my picture. I've got my copper wire that I can just draw out like this. Doesn't have to be gorgeous. Here's my copper wire, and it's being heated over a flame. So let me just draw a little flame out right here. Shoo, 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 flame. Yeah, it's a giant copper wire for a tiny little flame. Okay, so where is my heat transferring? Okay, think. Where does heat energy, what direction does heat energy transfer? Always goes from your high temp object to your low temp object. So I'm heating the copper wire over this flame, so my heat energy must be going from the flame into the copper. So I'm going to draw some arrows showing that it's heating it just like this. Remember, you have to use those squiggly arrows. Our squiggly arrows show energy transfer. Those singular arrows like this, that shows direction and motion of particles. We don't want that here. We're talking about energy transfer. So let's think about where this energy is going. Well, it's starting from our fire, and it's transferring to this copper wire. So the wire itself must be absorbing energy because it is taking energy from the fire. So think about your calculation. When you do your value of Q, what should you get, a positive or a negative, if your system is absorbing heat energy? Okay, so that's basically how I want these done. You're going to calculate Q up here, or calculate whatever I ask you to solve for in this first box right here. You're going to do your heat transfer model and explain it, and then you're going to go all the way down till you hit this problem right here. You're going to end at number 4. Once you're done, check your answer with the answer key, and you are good to go.